Okay, folks, welcome back. We are going to jump into page 2 now in our discussion about scatter plots and correlation. And now we're going to talk about measuring linear association. And this is actually going to be a new definition for us. And the word we're going to define is correlation. And that's a word that you probably have an understanding, an intuitive idea of what that means. But trust me, in AP statistics, it has a very specific definition that we will be using for the rest of the year. All right, to start our discussion about correlation here, what I want to do is look at the two sets of scatter plots here. We have one here on the left and then one here on the right. And we're asked which set of data has a stronger linear relationship. Well, just really quickly looking at the one on the left here, I mean, that's a pretty tight linear fit. If I try to sketch a line of best fit through there, and if I try to do the same thing on this other data set, I mean, the points are pretty far away there. So intuitively, your answer is going to be this one. You're going to say, yep, this one has the better linear fit, stronger linear relationship, because that line of best fit, those points are really close. But unfortunately, that answer would be wrong. The answer is neither, because they are the same data, just on a different set of axes. So that's if you look closely now, you'll see I kind of tried to fool you here. Take a look at the axes here, going all the way to -800, whereas this one just starts at 0 and then going up to 1600, whereas this one just goes up kind of the maximum of the data. So our eyes can be fooled very easily depending on the scale of our horizontal and vertical axes. So it's really important here. You should choose min and max values both on the horizontal and vertical axis to give you the best view of both variables. So let's make no mistake, this is the better graph here. This is the better graph because we kind of fill the left, right, and up, down you fill the available real estate in that graph with the scatter plot. And in the one on the left, there's a lot of wasted space. If your graph has a lot of white space like that around here, then it's probably not a real good graph. Okay, so the whole idea here that our eyes can be tricked based on how we choose the axes. What we choose as our scale on the horizontal axis and on the vertical axis means there's got to be a better way. There's got to be a better way for us to judge the strength of a linear relationship, and that's where correlation comes in. And the correlation, we use the symbol for correlation lowercase r. And I'm only writing that in just so that you recognize that's not just some kind of a typo. For the rest of the year, R represents correlation. And the correlation measures the direction and strength of a linear relationship between two quantitative variables. Holy cow, look at that. Let's pause for a second. Quantitative variables. So if somebody asks you a question about correlation and they give you one variable that's categorical and the other is quantitative, you should immediately call them out and say that's a ridiculous question, because correlation can only measure the direction and strength of a linear relationship between two quantitative variables. In the picture here on the right, there's just this is directly out of the textbook. There's a bunch of different values of correlation for different scatter plots, and we show one here with a correlation of 0, which means that there is zero linear relationship between those variables. Notice that it is the direction and strength of a linear relationship. So it's not a curved relationship, it's linear. So you can in fact have a scatter plot maybe that looks something like this. I'm just going to make one up. Let's say you had one that looked like this. That's a pretty nice curve, and we could probably fit an equation to that data, but the correlation would be near 0 because it's not linear. Okay, jumping back into these different values of correlation, here we see a kind of a weak negative association between that data, so that's why that value of R has a negative sign in front of it. Here's a positive 0.5, so I see kind of that upward trend in the data. -0.7. So as that value gets further, as the value of correlation gets further from 0, you should start to notice that the scatter plot, the points get tighter to that line of best fit. When we have a correlation of 0.9, they're getting pretty tight, and then negative 0.99, I mean, they're pretty much on that line of best fit almost exactly. So there's some things that are kind of revealing in that picture about the correlation value R, and I'd like to share those with you now. First of all, R can only be between -1 and +1 inclusive. If R equals 1, then we have perfect linear relationship. Oh boy, that's not how you spell perfectly. So let's start that over. Perfectly linear. And that's the same if R is equal to plus or minus 1. It's just a different slope. Positive being a positive association, negative being negative. If R equals 0, there's no linear relationship. Doesn't mean there's not a relationship, just means no linear relationship. Okay, so that takes care of this first bullet. R has to be between 0 and 1. We've already kind of talked about this. If R is greater than 0, the association is positive. If it's less than 0, the association is negative. And what R does for us is it quantifies strength. And I'd like to kind of give you a picture of how it quantifies strength. And this is kind of an image that I've used the last couple of years to say, okay, let's talk about correlation on a scale. And we're going to start by talking about what if the correlation is 0. And the strength of that would be none. There's no linear relationship if the correlation is 0. And I'm going to jump out here to 0.3. What if the correlation is 0.3? Well, that's pretty weak. What if I get up to 0.6? I'd start to use a word like moderate to describe that. And then we get out here to 1, which is strong, right? So it's kind of a continuum of values in a continuum of words that we would use to describe the strength of a linear relationship. And you have to pick, you kind of have to choose a descriptive term down here based on what the correlation is. So we're going to use terms like no linear relationship, weak, moderate, or strong, depending on where that R value falls. And we have to do the same thing for the left-hand side of the number line as well. So if we have a correlation of negative 0.3, that's pretty weak. Negative 0.6, we're starting to get into that moderate range. And then perfectly linear out here at -1, that would be strong. Okay, so let's see correlation in action. We're going to go back to the track. Here's a scatter plot of that sprint time and long jump distance that we talked about on page 1. And the correlation for this data set is negative 0.84. And we're asked to interpret the value of R in context. And anytime we're asked to interpret R in context, we have to both talk about the direction and the strength. So good interpretation of that negative 0.84 would be this. We have negative association, and it's pretty close to the absolute value there. And some of you are like, wait a minute, you said there'd be no algebra in this course. But yeah, the further away you get from 0, the stronger that relationship is. And so this value of R, the absolute value of that, is getting pretty close to 1. So we'd say that's a negative association because of the negative sign, and then a strong linear relationship because we're getting close to the absolute value there. It's getting close to 1. Okay, so let's now take a look at a specific point in this scatter plot. What effect does the highlighted point have on correlation? So do you think this point here improves the correlation, or does it make correlation worse? And let's take a look. I'm going to sketch a line of best fit through this data, and that's just a sketch, a sketch of what I think the regression line might look like. And then let's see. That's pretty far. This point is pretty far from the regression line. So my guess is that without that point, so if we got rid of that point, I think that the correlation would probably improve. And let's see if that intuition is correct. So the highlight point is further from the estimated trend line than a lot of the other points. So that point actually weakens the correlation. Without that point, if that point were removed, the correlation would improve to negative 0.87. Not a huge change, but it's definitely follows what we would our expectation there. Okay, that's enough for page 2. We're going to shut this one down and then pick up page 3 shortly. Don't forget, I mentioned that this was out of 4 pages.